We had a definition of a dipole moment. The electric dipole moment in the presence, no, just the permanent electric dipole moment, no time dependence, nothing like that. We had it 2 weeks ago as being the expectation value of the dipole moment operator and the wave function. We derived that in 2 ways, 2 or 3 ways actually. We derived it one that we first looked at the classical expression for dipole moment, generalized that to not point charges but the charge distribution, which that meant that we ended up with an integral. And to sort of recall that, we had an expression for a dipole moment which was the integral over r times the charge distribution, like this. Integral over all space, here r, and then the charge distribution, which shows that a dipole moment is actually the first moment of a charge distribution. Now replacing that charge distribution for the electrons by Born's interpretation of a wave function, that the square or the absolute square of the wave function is actually the probability for finding an electron, so it's the particle distribution. We can, from there, we can get to this. We also looked at the Hermann-Feynman theorem. If we define the dipole moment as the first derivative of the energy, using the Hermann-Feynman theorem, we also end up with an expectation value. Because the Hermann-Feynman theorem tells us the first derivative of the energy with respect to some parameter in the Hamiltonian, and that parameter would be a field strength, is just the expectation value of the corresponding derivative of the Hamiltonian, which gives us that. And there is actually a third way to get to this using time-independent perturbation theory, where the first energy correction is actually the expectation value of the perturbation operator. That also brings us to that. So in the static case, that's the way we calculate dipole moments. Now we have a time-dependent case. So how do we generalize that? Well, that's very simple. Now our wave function is time-dependent. So we have obviously a dipole moment which changes with time. And it changes with time because the induced dipole moment due to the field depends on time. That's oscillating. And therefore we get a permanent contribution. That's this one. Plus we get an induced dipole moment. And that induced dipole moment is then time dependent. Induced by a time-dependent electric field. Now if we use that the time dependence of the field can be described in this way, then obviously that induced dipole moment will show the same time dependence. And then one writes that as, again, an integral over all frequencies. Here the frequency components of the field, cosinus of omega t, t omega. And then remember the induced dipole moment was the polarizability tensor times the field, and that's the same here. We have a polarizability tensor, but that polarizability tensor is now frequency dependent. So that's the classical description of a dipole moment in the presence of an oscillating, this way, time-dependent electric field. Where we here have the generalization of the polarizability we had before to now a frequency-dependent polarizability. Sometimes they're also called susceptibilities. I think the UPAC notation or nomenclature is, if you talk about a susceptibility, you're talking about a macroscopic property. Whereas if you talk about microscopic of individual molecules, you talk about polarizabilities in the electric case and magnetizabilities in the magnetic case. So that's the property we are aiming after. We want to describe this. We want to get quantum mechanical expressions for this frequency-dependent polarizability now. So how do we do that? Well, we basically go back to this, but have to generalize it to the fact that now we have all time-dependent. So our dipole moment now is the time-dependent dipole moment we then just calculate as the expectation value of this time-dependent wave function. Like this. And in order to get the polarizabilities, to get an expression for the polarizability, what we do now is we insert whatever expression we have found for the time-dependent wave function in the presence of the perturbation, in the presence of the field, which in our case is this here, with that and that contribution, and plus more. We insert that in here, and then we try to identify what corresponds to this term. And that's going to take a bit of time, but let's do that. Let's get started on that. So obviously, we can see what the polarizability, being in the static or in the time-dependent, frequency-dependent case, is the proportionality factor. I mean, it's not a factor because it's a tensor, but still, it's a proportionality factor to the field, to the first power. So it's linear. It's in the linear contribution of the field. And that means, if we think about the expansion of this expectation value, in orders of perturbation, 0 first order, what we're going to look at now, or we're going to have to find, is a first order correction in this. Because that first order correction is going to be linear in the field, so it must correspond to this term in some way or another. So the first thing we do is, therefore, we insert our expansion and keep as many terms as necessary in order to describe this, which in our case means we have to keep the first order terms. So our time-dependent dipole moment is then, and I have to insert the wave function in two places. So let's start with the pure zeroth order term. So that's going to be my dipole moment operator, and instead of looking at the whole vector, I want to look at an alpha component now, x, y, or z. So I have the alpha component of my operator. I have the zeroth order correction to the wave function. That's the zeroth order term, which is here. So I have E H0 T divided by I H bar and my unperturbed ground state wave function. In the cat, I also have to put it in the bra, but remember the bra is complex conjugate. That's normally not something we really think about it, but now I have this extra phase factor, time-dependent phase factor in there. If I write it in the bra, I just can write it as it is. If I take it out of the bra, and that's what I want to do immediately, I have to complex conjugate it. And since that thing is complex, because it has the I down there, I'm going to get, instead of I, minus I. So I'm going to get e to the minus h0 t divided by I h bar. That's all zeroth order, so that's a zeroth order contribution. Now, let's immediately look a bit more at that term, because that does not yet look like this one, which is permanent dipole moment, because I have these two exponentials in there. But this is a Hamiltonian, that's the unperturbed Hamiltonian. And these are the eigenfunctions to that Hamiltonian. So I can do two things here. I can either let this one act on this one, and instead of h0 I get e0. Can let this one act on this one, and instead of h zeroth order Hamiltonian I get e0. And then I can take the two exponentials out of the Hamiltonian, and here I have plus, here out of the matrix element, out of the integral, and here I have plus and here I have minus, which means they cancel. That gives e to 0, which is 1. So this, they eventually actually go out. And that's sort of the reason why we normally don't consider this phase factor if you have no time dependence otherwise in the Hamiltonian. Because if you just take matrix elements with eigenfunctions, they always go out. Because I have the complex conjugate, so I get a minus, and then the whole thing disappears. Now, first order. The first order is going to be a zeroth order here, my dipole moment operator, and the first order there, plus the complex conjugate all of it, because I have to insert, now I insert the first order here, but I also have to insert it there. So I also get a first order dipole moment operator. Zeroth order like that. Those are the two, there are two first order terms. And everything else what comes now is going to be of at least second order and higher orders. And since I'm only interested in terms linear in the field, I can stop here.